Welcome to Understanding Climate with Professor Monks. Today's topic, sea level rise. One of the most well-known impacts of climate change, besides higher temperatures, is sea level rise. Climate models predict that the oceans could rise as much as a meter in the next century, and more after that, depending on our emissions. Understanding sea level rise requires understanding the dynamics of the cryosphere. The cryosphere, from the Greek for ice, means the components of our Earth system that are frozen. These include the huge continental ice sheets of Antarctica and Greenland, smaller mountain glaciers around the world, sea ice in the Arctic and Antarctic seas, and permafrost, permanently frozen soil, in northern North America and Eurasia. Let's start by looking at sea ice. This is ice that's floating on the surface of the water. When the Earth heats up, the sea ice starts to melt more in the summer than it refreezes in the winter. We can document the reduction in sea ice around the North Pole. It's one of the clearest indicators that our climate is already changing. The melting is so significant that the Northeast Passage around the northern coast of Siberia and the Northwest Passage around the northern coast of Canada are becoming open to shipping. The sea ice loss also creates an albedo feedback. Open ocean has a lower albedo than ice, absorbing more of the sun's energy and further heating the Earth. But melting sea ice does not change the overall sea level. The ice is already in the water. It's the same reason that if you have ice cubes in your drink, when they melt, your drink doesn't overflow. But ice on land is a different story. The underlying ground holds the ice up out of the water. If the ice melts and runs into the ocean, that adds water to the ocean, causing the sea level to rise. When we look at small mountain glaciers in places like the Alps and Rockies, we see clear signs of glacier retreat. Old photographs and records show that these glaciers used to reach much farther down the valley than they do today. These mountain glaciers are important to the local ecosystems. Many people live in areas like the Ganga Valley in India, where rivers are fed by the seasonal melting of glaciers, so they could be left without water for their farms and households if those glaciers disappear. But mountain glaciers don't have a huge impact on global sea level. What makes the big impact on global sea level is the huge continental ice sheets in Greenland and Antarctica. Of the two, Greenland has been melting faster in recent years, because temperatures in most of Antarctica are still below freezing. The Greenland ice sheet contains an estimated 2,850,000 cubic kilometers of ice, while Antarctica holds 226.5 million cubic kilometers. The rapid melting of Greenland's ice is one possible explanation for the localized negative temperature anomalies often recorded in the North Atlantic. Adding all of this cold meltwater to the ocean is counteracting and pushing away the normally warm Gulf Stream current. Melting of land-based ice accounts for a little more than half of sea level rise, both observed sea level rise so far and predicted sea level rise in climate models. The other half is due to what is called thermal expansion. When water, like most materials, is heated, its molecules bounce around more. This expands the volume of water just a little bit. It's not enough to be noticed if, say, you heat a pot of water on the stove. But when you add up this tiny expansion across the volume of water in the entire ocean, it becomes significant. A little under half of the observed and projected sea level rise is due to this thermal expansion of the water already in the ocean. Depending on which scenario we follow, climate models predict somewhere between half a meter and a full meter of sea level rise by 2100, though there are larger uncertainties here than with temperature changes. A meter of sea level rise could flood many coastal areas. Low-lying places like Bangladesh and the Netherlands are at high risk. Countries like Kiribati and the Maldives, which are made up of coral islands that only stick out of the water a few meters, could be lost completely. Port cities all around the world are major hubs of transportation and trade and have huge numbers of people living close to sea level. And even if a coastal area isn't submerged by sea level rise increases the dangers from storm surges during hurricanes and other extreme weather events. This is especially dangerous if sea level rise damages coastal landforms like mangrove swamps and low barrier islands. These landforms absorb storm energy and shelter people living on the inland side from storm surges. Another hazard associated with sea level rise is saltwater infiltration. People and crops rely on groundwater found in aquifers and soils below the ground. Seawater seeps into the ground, bringing salt into groundwater reserves that are at or below sea level. Groundwater above sea level is generally fresh because it seeps in from rain and streams. Rising sea level brings salty water higher up, potentially affecting drinking water wells and the roots of crops. Heavy human withdrawals of groundwater exacerbate this hazard even more. If people pump up the fresh water from an aquifer, it leaves a gap that salty ocean water flows in to fill. The variety of hazards presented by sea level rise mean a variety of strategies would be necessary to adapt to it. Some critical infrastructure may be protected by dams and seawalls. Farmers affected by saltwater intrusion may have to switch to more salt-tolerant crops. In other places, the only solution may be to move away from flooded areas. The nation of Kiribati is already buying up land in other higher elevation countries for its people to move to. People forced to move because of climate hazard like sea level rise are called climate refugees. Many scholars and activists argue that international refugee laws, which were designed to deal with people displaced by wars and genocides, need to be updated to account for climate refugees. The study of the Earth's long-term history shows a pretty straightforward relationship between sea level and temperature. For every degree that the Earth's temperature rises, sea level goes up by about 20 meters and vice versa. But climate models show only a meter of sea level rise accompanying a 3-degree temperature increase by 2100. What gives? The answer is that it takes a long time for sea levels to adjust. Ice takes time to melt, and heat from the atmosphere takes time to propagate into the deep ocean. If we were to let climate change reach 3 degrees by 2100, but then stop all further temperature increases, sea level rise will continue for centuries until it reaches equilibrium. Florida might not be totally underwater in your lifetime, but even if we solve the climate crisis today, it's a problem that future generations will still have to address.